Welcome to Data Science with EJD. We're still talking about reinforcement learning, which is a branch of machine learning, just like supervised learning and unsupervised learning. Like we said already, reinforcement learning involves having an agent in a particular state and with some available actions, and then the agent takes the action and then gets certain rewards, and that reinforces some behavior and discourages some other kinds of behavior. So in this video we're talking about deep reinforcement learning. So of course, there's deep learning, right, which involves neural networks and things like that. So it's more like you have reinforcement learning at the level of neural networks, something like that now. So why do we have to talk about deep reinforcement learning? The motivation, first of all: classic reinforcement learning struggles with large or continuous state spaces because it relies on tabular representations. Many real-world tasks, e.g., robot vision, self-driving cars, Atari games, have high-dimensional raw input. For instance, images. So the solution to do this is want to combine deep learning with reinforcement learning, and that is what leads to deep reinforcement learning. And this use neural networks as function approximators, right, for value functions or policies. The key breakthrough is that deep Q network, DQN, like with DeepMind, done by people like bodies like DeepMind 2015, learn to play Atari games directly from pixels, right? So how deep Q networks works, right? How DQN works, deep Q networks, how that works. So core idea is that you approximate the optimal Q function, Q star, given the state and the action, and that approximately gives you something, with a theta parameter using a neural network with parameters theta. So the workflow is such that you have a state and you have a neural network, which leads to prediction of Q values for all possible actions. And then you select action using epsilon greedy policy, mostly exploit and sometimes explore. Then you execute action, observe reward, and next you move to the next state. So then you store the state, the action, the reward, the next state, and done in replay buffer. Then sample mini batches from buffer to break correlations and update the Q network using temporal difference loss. Then we have the stabilization techniques. So experience replay. So this decorrelates samples, improves data efficiency, and you have the target network, a slowly updated copy of the Q network provides stable targets for training. Then we have key extensions to deep Q networks, right? Double DQN, it addresses overestimation bias by decoupling action selection and evaluation, and it uses online network to choose best action, target network to evaluate it. Then you have the Dueling DQN, which splits the estimation into state value V of S and advantage A of S, comma A, and it helps the agent learn which states are valuable regardless of action. Then you have the prioritized experience replay. So it's more important transitions with high temporal difference error are sampled more often, and it increases learning efficiency, especially for rare but significant experiences. Then, what are some limitations of deep Q networks? It is not ideal for continuous action spaces, so it needs discrete actions and can be unstable and sample inefficient for complex tasks. It is sensitive to hyperparameters like learning rate, buffer size, and epsilon decay, etc. It's solved by more advanced methods like actor critic, A3C, PPO, DDPG, and SAC. Then let's try to implement. Of course, I've discovered that anytime I'm doing anything close to deep learning, it usually requires some computing capacity, that will be beyond my computing power in this situation. But I'm just going to explain the process as much as possible and see how far the code goes, because the code just takes a lot of time to run. Okay, so implementing deep Q networks, solving CartPole. I mean, so far we've talked about things like frozen lake, cliff walking, and now we're talking about CartPole. So below is a clean PyTorch implementation that puts all ideas together, all the things we've talked about, right? So I imported one in to filter out any warning that may just not that may be an issue. So of course we import gym, NumPy, random collections, where we bring in DQ, and then we import torch and torch neural network. Anytime you are doing deep anything, neural network has to come in. Then torch.optim as optim, then matplotlib.pyplot as PLT, like that. So then you define the Q network. So using object-oriented programming, we define a class called Q network with NN module, and we initialize all that. Then we have the hyperparameters, the environment, gym.make, the CartPole v1, state size, action size, we have all that. Then we have all the other conditions, epsilon, decay, epsilon, n, and all that. Initialize networks, optimizer, replay buffer. Then you have the epsilon greedy policy from line 49. Then you have the training loop and all that. So you have the decay epsilon in 107. Then update the target network. So this is going to take a long time to run. So let me just start the process. Let's see the first few results, and then we can move on. Let's see. Does it begin to produce any results? Yeah, okay. So we have all the epsilon 0, reward 33, epsilon is 0.995. You see, then right now we have, I mean, it's a lot. It's going to like 500 episodes, I believe. Let's see where we stated the number of episodes we should have. Yeah, number of episodes in line 40, that's 995. So epsilon decay 0.995, epsilon and 0. So from 0.995 should decay to 0.01. That is what this means. The epsilon start, target update frequency, and all this buffer. So I mean, all this keeps going on like this. So it's until it gets to 500 episodes. But in running it, I usually got some breakdown. So you see the reward 282, the reward is now 51.0, and the epsilon is 0.242. And we want epsilon to go as low as I think 0.01. So it just keeps going. So I'll just go on and come back later to see what happens. So you can experiment with hyperparameter tuning, right? So you can adjust the learning rate, the batch size, that size of update batches, the epsilon decay, which controls exploration stroke exploitation trade-off. Then you can look at the target update frequency, how often the target network is updated. Then you can observe stability of learning curves, how quickly it reaches average word of greater than or equal to 195, right? Average word of 195. So we see the reward fluctuating here and there. So far it has got to almost 400 now. So we'll come back later. So the next steps you can do, you can extend to double DQ, deep Q networks and modify target Q value computation, then add dueling architecture and split into value and advantage streams, then use prioritize replay buffer, try on more complex environments like mountain car, lunar lander, or Atari games. So these are some environments. So we've seen frozen lake, we've seen cliff walking, now we've seen the situation here now. What's that again? Let me try to remember. I think it's CartPole, yeah? CartPole. So yeah, we are nearing it's at 459 now. So we are nearing, okay, so the reward has been consistently 500 this time around. So so the outcome, with this harmonized module, you now understand why uh deep reinforcement learning is powerful, how deep Q networks, you know, how deep Q networks works technically, and how it enhances. Okay, we have a story there. Deep reinforcement learning appears to have died. It will restart. So he said because of but for some reason it doesn't get to the end. It gets to like 499 and stops. But already we already have a fair consistency of 500 rewards, and then we also been having some consistency in the epsilon to be 0.082. That can be a fair way to go. Then we have also seen how it enhances fixed weakness, how its enhancement fix weaknesses, and how to build, train, tune, and visualize these agents, right? So those are some lessons we have learned in that scenario. Okay, so of course, this has broken down at some point, so we are good. We can as well just let it be. So with this, I come to the end of this video. Let me know if there's something you like me to try out. There's an idea you think you want to try out. Let's see to that. And if you have subscribed already, I appreciate you so much for that. If you have not subscribed already, please go ahead and do that right now, because you have a whole lot to gain here. So click on subscribe and hit on the notification bell also, so you can always get alerted each time a new video is released, right? You can also become a member of my channel at 3 different levels currently. All right, so you want to become a member so to get some extra perks as a member of the channel. So but of course the code sheets that I use for this for all the things I do, they are available on Google Drive. Just look at the link in the description, either on Facebook or on YouTube, so you can have access to my code sheets, my data sets, and even my slides for the introductory lessons, right? So be sure to like and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing data right. Bye.